Deepak is going to talk about entropy and non-entropy.
Okay, thank you. Yeah, so it's a great pleasure to be here, and let me thank all the organizers for inviting me here. In this talk, I will discuss entropy and non-ergodicity. I take a simple model of many sokobans and boxes on a line. I'll define the model. So this work is done with the student Priyadarshini and Abhishek Dhar, and we benefited with lots of discussions with Diptiman Sen at IISc. So this is the outline of the talk. I start with the introduction, which is sort of the motivation for the work, and then define the model, and then I'll discuss the phase space decomposition and a little bit detail about how we calculate the sizes of sectors and numbers. And then there is, we will discuss the definition and calculation of non-equilibrium entropy in this model, and some concluding remarks. Okay, so this is the motivation part. In many disordered systems such as glasses and folded proteins, the canonical equilibrium statistical mechanics approach using partition function fails. And this is because of non-ergodicity. The system explores only a small part of the phase space. The time averages of observables at experimental time scales are not equal to phase space averages that are calculated in equilibrium StatMech. Okay, so in this context, a very useful but heuristic way to understand this behavior. This is a very old picture for a long time, but it is called complex energy landscape picture, and it is schematically shown like this. The x-axis is called configuration space. It is very high dimensional, but y-axis is the energy. And what is shown here is that you imagine that in some system there can be a very large number of minima, and if the system is stuck in this part of the phase space, then it makes small excursions around there, but doesn't go to the other minima, and it samples only a small part of the phase space. And the red line here shows sort of the energy of the system at a particular time. And what you would like to know is, so if you change the E, then this accessible part will change, of course, and this is what we would like to understand. Okay? So just because this system spans only a small part of the phase space, it says the variance of quantities is typically less than it be found if you took sample over the much bigger thing. And so, for example, if you calculate the variance of energy, that's called the specific heat. Specific heat in a non-equilibrium system is less than in equilibrium, and integral of that is the entropy. So the entropy change in a non-equilibrium system is less than in equilibrium. So here, this is a picture of liquid, and if it became a solid, it would have this, but in non-ergodic systems like glasses, it is, it looks like that. Okay. So this picture of landscape picture is very useful and qualitatively correct, but it has been very difficult to use this to make quantitative predictions. To make quantitative predictions, one needs to be able to calculate the number of minima, distribution of sizes of basins, and basins of attraction. And meta basins are collections of, if the energy is big enough, then you don't stay in one basin, you can go to several basins nearby. And so you should be able to calculate this as a function of energy. And usually it is not possible to do this in any non-trivial model so far. So what we'll try to do here is discuss a toy model of sokobans and boxes showing non-ergodic behavior, where this calculation can be done exactly, and the number, sizes of accessible regions can be calculated. And it is sort of like what in India it is called CAT scan. I think the standard name is CT scan, but CT scan of phase space. And the doctors call it CAT scan. So the A is not really there. Okay.
But so some models for which you can compute the number of minima at a given energy, like mathematicians, for example, typically look at these Gaussian models or something.
No, so those are by definition. Not they don't calculate. They postulate that this is what the distribution energy is a Gaussian.
No, I don't mean that. I mean you have a Gaussian landscape with a given covariance function, and then you can actually calculate in many cases, some cases, at least in spherical concept, Wiener rules, the other people, Cerny and all these people. So
okay, no, so, for spin glass literature, it is not really much there, but yeah, in one sort of some models, it can be done. So, the definition of the model. Sokoban is a video game invented by Hiroyuki Imabashi in 1981, and you can download it free from the internet. Just say Sokoban, and it will come there. Anyway, it features something like this. A Sokoban is a warehouse keeper, that is this guy. It can move around on this lattice and one space at a time, and it can push these boxes, yellow squares, and the game involves pushing these boxes into the red crosses, and if you can do it fast, then you get more points. That is the game. The Sokoban can move empty spaces and push boxes if the next space is empty. If it is not empty, you cannot push. Okay, so this model was defined earlier by Bonomo et al. In 2024, and they considered a single blind Sokoban moving in a random background with a given density of boxes. So there was one Sokoban, as in this game, and the boxes are placed at random, and there is a given density, and they ask what happens. So it's called blind Sokoban because the Sokoban has no strategy. In the real game, you have to have strategy to go from here to there. But in the blind Sokoban, it just tries at random and sees, if it can push it, it pushes with some rate. And so can push an obstacle to the site in the direction of motion only if the site is empty. Since Sokoban can push objects out of the way, one would expect her to get trapped less often than a blind ant in the Dijon ant in the labyrinth model. So this is a very famous model, Dijon ant in a labyrinth. If the density of boxes is very high, then the ant gets confined, and if the boxes are few, then the available space is bigger, then it can go all the way. So, but interestingly, it was found by Bonomo et al. That in this model, even if the density is very small, like 0.1%, then in 2D, the ant actually gets confined. So if the sites with no obstacles form a spanning cluster in the percolation problem, the Dijon ant has a mean squared deviation that increases linearly with time, but the Sokoban traps herself with probability 1 on the square lattice. The probability 1 part is not sure, but numerical simulations suggest that that's what happens. And we will study this model in 1D. In 1D, the Sokobans always get localized, and so the localization, delocalization transition is not present. Okay, so this is the definition of the model. We consider a model on a line, but with many Sokobans and many boxes. And much of the discussion can be also extended to higher dimensions. So here is a line. The yellow squares are the boxes. The pink circles are the Sokobans. The Sokobans can move to an empty space or they can push the box. So let the density of Sokobans and boxes be rho S and rho B. A configuration is specified by a string of the form EESE like that. And the transitions allowed are ES can become SE and SEB can become EBS. And the reverse way, if the Sokoban is on the right, then it can push the box to the left. E stands for the empty space, yeah. How to characterize long time steady state of this system in the large lattice size limit? That's our question. Okay, so some features of this problem are quite easy to predict. If we start with a random configuration of Sokobans and boxes, there will be stretches with more than 2 boxes between 2 consecutive Sokobans. Okay, so there may be Sokoban here, but they mean several boxes. Then the rightmost of the boxes in the stretch can only be pushed to the left, and the leftmost, yes sir. The Sokoban just moves at random, so they try with rate 1 to go this way or that way, and if they can manage, they do it. So, the rightmost box can only be pushed to the left, leftmost to the right, and finally we have a structure like the two boxes come close, but once they become two boxes, you cannot push them. So they become immobile, and they remain there always, and they are frozen and they cannot move. So that is the mechanism of setting of freezing in this model. And of course, where they become stuck is random, depends on how you move them. So the line gets divided into active regions with Sokobans and empty spaces, and singleton. So suppose there are two boxes here, this cannot change and this cannot change, but in between in this region, the Sokobans can keep on moving and they can keep on even pushing the singleton box around. So the line gets divided into active regions and frozen regions. And so there is a strong breakdown of ergodicity in this model. The phase space breaks into a large number of mutually disconnected components.
One question is, Sokoban can push the box left or right, both ways?
No, only in the forward.
Or only the right way?
No, only forward. If the Sokoban is on the left, then it can push it to the right. If she is on the right, he can push it to the left.
So, but two consecutive boxes cannot move.
Two consecutive boxes cannot move.
What happens if there is a box and there are two Sokobans on both sides?
It cannot move until the Sokoban goes away and makes space. Okay, so the total number of configurations is 3 to the power L, because every side can be 3 states. The number of disconnected components grows exponentially with the size of the system. So this is easy to see, because at least in the case where there is no Sokoban, there are only boxes and empty spaces, the number of states is 2 to the power L, and each of them is a totally stuck and separate component. So the number of components is more than 2 to the power L. Yes, sir.
So if there are two boxes, it cannot move.
Yeah.
So this will be broken by definition.
Yes. Okay. So now we come to characterizing this thing. Existence of conserved quantities, constants of motion. Sometimes they are called constants of motion. So clearly, the number of boxes and number of Sokobans is conserved during the evolution. So these two constants imply that the phase space breaks up into order L squared disjoint sectors, because the number of Sokobans can take at most L values and the number of boxes can take at most L values. So there are at most L squared sectors you can make with these two constants. So there are many more constants of motion. And for example, the relative order of S's and B's cannot be changed under the dynamics. So this is called the irreducible string, and so it says that if you take a configuration, you just get rid of all the E's in the configuration, and you get the irreducible string is removing the E's, and under the dynamics, this irreducible string will not change. And so irreducible string is a constant of motion. Okay? But the irreducible string can take a large number of distinct values. The number of irreducible strings of length L is 2 to the power L. And so, you get 2 to the power L disjoint sectors. The constancy of IS is equivalent to order L independent constants of motion, because you can say the first element is constant, second element is constant, third element is constant separately. But this still does not explain the full structure of the phase space breakup, and there will be additional constants of motion in this problem. The allowed transitions may be represented by a directed graph on the set of vertices, denoting different configurations. So you just imagine 3 to the power L points, and from A you can go to B, there you draw an arrow, and then we are asking what is the set of this directed graph, what kind of allowed transitions are there. And we are able to characterize this graph fully. So this, yes sir. Yeah.
When you begin, these are things that cannot be
Yeah. Yeah, no, so very good. Yeah, so, very good. No, you are right. So there are actually two different things. One is the constant of motion which remain constant throughout. And the other things are things which become constant and then they cannot go out. They are called attractors in general in dynamics. So this thing also has attractor parts and there are constants of motion. And yeah, okay, so anyway, let me not discuss that here now. The breakup can be seen as a three-stage breakup. In the first stage, the graph breaks into disconnected components such that no directed edge from one component to another. In the second stage, using the irreversible nature of some moves, we can organize the configuration into one connected component. You just take one connected component, then you can break it up into levels, 1, 2, 3, such that configuration at level R can only stay at the same level or move to a level below. And R equal to 0 are recurrent, they cannot go any further, they just keep on moving at the same level. Within the same level, you can further subdivide it into mutually disconnected components. Okay, and so this is schematically shown in this picture here. There are vertical lines. So, each dot represents a configuration, and vertical lines, there are no arrows between them, but then you take one component, it can be broken into levels. You can only go down or stay at the same level, and within the level you can stay, these four can keep on moving amongst each other or so on.
What are these numbers in vertical level?
This is the height of the level. 0 is the ground floor and first floor, second floor. No, so this is, so you can actually take any graph and you can find subspaces which you can get in but not get out, and find the sort of maximal set of such things, or the minimal set of such things. That's the ground floor. You can get there but cannot get out. Then there are states which are one level above. You can get to the ground floor in one step, and that's level 1, and then level 2 and so on. Then within the level you can say you cannot go from here to here, because there is a connection of this, but it's only through other levels. So that is the third stage of decomposition. Okay, and here is an explicit example for one connected component L equal to 6. You can start with this state, it can go here, it can go here, and so on. The details are not so important, but the level structure you can actually work out for any given L explicitly. Okay, so the first stage of decomposition. Now we want to characterize this in more detail. At this first stage of decomposition, we are only looking at are there connections between states, and it's allowed to make all moves reversible. Then the Sokoban can both pull and push boxes. And so we make the change of rules. SE can become ES, and BSE can become EBS. It can also pull. So in this case, there are still extra conserved quantities beyond IS. And if there are 3 boxes one after another, between some empty spaces in between, then the middle box cannot move, because the Sokoban can only push it, okay, or pull it back, but it will not be able to move the middle one. And so that's an extra constant of motion. Sorry? So here this can move, it can push and pull. This is the box in Sokoban, this can be, it can pull it and move back. Okay, so we may denote the position of immovable boxes by capital B, and then the configuration looks like this. The same string, but you can identify immediately what are the boxes which will not move in space ever. Then the boxes, positions of big B's and the irreducible string of parts between the B's can be separately conserved, not only the full irreducible string, but between any 2 big B's, the string is conserved. And this actually exhausts all the conservation laws. And we use this to actually determine the number of disconnected components. And it grows as 2.28 to 88 to the power L. We'll show this, but it's just the result is that it's much more than 2 to the power L. And that's because of these extra conservation laws of big B's. Okay, second stage decomposition. Now, if there are two boxes separated only by empty spaces, there is at least one Sokoban neighbor of one side, then this spacing can only decrease. Now we are back to the case where you can only push and not pull. Then the spacing can only decrease. Then if you have two boxes and the spacing can decrease in the sense there is one Sokoban on the left, then you just count how many spaces are there. And it will keep on decreasing, and it will become 0 at some stage eventually. And that is called, by definition, the total number of such spaces is called the height of the configuration. So number of contractible spaces is the position of one box and another box, and summed over boxes, pairs, such that at least one Sokoban on one side. And clearly under the move, HC can only decrease or remain the same. And now we can determine the number of configurations at a given height. At the second stage of decomposition, each component breaks into at most order L different things. So this number is still 2.28 to the power L. It doesn't change. The third stage of decomposition, in stage 3, we note that the configuration at fixed height can be broken up into disjoint groups, such that within a group you can go from one set of one configuration to another, but you cannot jump. And so these we call intra-level connected clusters. Identifying ILCCs is straightforward. One has to modify the definition of frozen region and treat all contractible spaces also as frozen. If there are two B's, then there is some space between them. If they are going to stay at the same height, this space cannot change. So even that is a frozen part for discounting. So that's how we calculate this number. Let me just give the indicate how this calculation is done. Let's calculate the total number of disjoint sectors in the set of recurrent states. So any particular configuration has a structure active, frozen, active, frozen, active, frozen, where a particular connected region is specified by a class of mutually accessible configuration. If you are in this A region, then there you can tell what are the allowed configurations in this A region. F is frozen. To each active region, we assign a unique standard configuration obtained by pushing all the empty spaces as far to the right as possible. And then you count the number of standard configurations. Okay? So then a formal sum over all possible strings of standard configurations is A equal to A, infinite string. But this can be written as S into one, S followed by either S or BS, as often as you like, and then followed by E's, as many as you like. And so then we take this and substitute X for each symbol, and you get a generating function for A is given by this formula. Similarly, F can be found by summing over all possible strings which are frozen strings, and you get F equal to some series like this. Sum over all possible strings is of the form something on the left, A, F, A plus AFA plus AFA, FA plus like that. And this can be written as A over 1 minus AF. And so this is the full string, and the condition for singularity is AF equal to 1. And A and F are rational functions of X. And so this becomes a polynomial equation by solving. And you can show that the total number of configurations is these components is 2.32 to the power L. And some modifications of these, you can show fully disconnected components, which we already showed. And number of components after third stage of decomposition is something like this. and a number of recurrent configuration goes like that. Anyways, the calculation for fixed densities, other densities can be done similarly by introducing weights UVW as conjugate Lagrange multipliers in the generating function. That we will not do. It can be.
Finite is
Yeah,
boundary condition.
Those are, you have to open. Okay, for example, the number of disconnected components you can calculate is some, we already gave the generating function. And after stage 2 decomposition, this was some number like this. But this breaks up, this is 0 level, first level, second level, third level, and so on. And I cannot write it at the third level, it becomes a little bit messy. But entropy per site as a function of the height, h by L. And this is the density of contractible spaces, this is the entropy per site, and initially it increases and decreases. The maximum possible number of contractible spaces is, fractional number is 1, because you could just have one S and B and then another B at the end, and it can push all the way. There are very few of them, so that the entropy is very small. Okay, calculation of non-equilibrium entropy. We characterize the macro state of a system in terms of some macro observables O1, O2, O3. Number of microstates consistent with this macro description is called omega total. In the generalized microcanonical ensemble, all these are assumed to be equally likely, and we define the ergodic entropy as S equilibrium as log of this. This is the Boltzmann formula. For each microstate in this GME, we define omega non-ergodic C as the number of microstates that can be reached from C within reasonable time. Similar to the recent proposal of Goldstein, and
What does it mean by reasonable time?
that's not easy to tell. Now, there is a little bit of sloshiness in the definition, but we'll have to work with that. We define non-equilibrium entropy as the log of this average over C. Take a random configuration, what is its entropy? For large systems, we find that this entropy so defined is extensive, and there is corresponding entropy density, and that's a function of the densities of macro observables. So a large L limit is being taken here. And clearly the non-ergodic entropy is less than the equilibrium entropy. We can define the difference between these to be the temperature dependent configurational entropy, that is the terminology used in glasses. Sometimes people use the word frozen entropy in ice and so on. So we note that the definition here uses only the notion of accessibility between configurations and not the actual time required to go from one to the other. And so it is kinematic and not kinetic. We are not doing dynamics actually. Of course, the model was defined with dynamics, but in the calculation of entropy, you just say this configuration can be reached from this. I don't care how long it takes, so long as it's in the reasonable time. So it is important to note that in non-equilibrium systems, the alternate definition, which is given by this Gibbs definition. So you have some system, it occurs in state I with probability pi, then this is the Shannon-Gibbs entropy for the state. This definition is often used in non-equilibrium state mech, but this definition is actually not really valid or good, and it doesn't work, at least in some cases. And so this is important for students to note. It's not my own observation, this is given in Goldstein et al. Earlier. In the situation where one may have many different possible macrostates, it should be possible to define the probability that the system has an entropy S. So I take a pot and put some water in, put it on the heater, either boil it at low heat or high heat for 1 minute. What is the end state? It should be possible to say that with probability half, the end state has high entropy, with some probability it has a low entropy. But if you use this definition rho log rho, or pi log pi, there is only one number you can give. You cannot give probability that the entropy has one value or probability has another value. And that is a major shortcoming of this definition. Yes, sir.
In non-equilibrium, because this is only the system part, right? And in non-equilibrium, they also include the other part which interaction with the path, right? And this in your heating, you are not including that part. No?
So right now we are discussing the entropy of this thing,
System,
whatever it is.
right?
Yeah.
No, I'm saying that's why this your heating example, it does not work.
No, no, I'm only asking that, okay, I did this experiment of heating up water at time t at the end of the experiment. What is the entropy of this thing? I don't care how it was get there. The answer is this entropy, using this formula, can only have one value. But I will like to say that with probability half it has this value and with probability half has this value. And actually the value you give is not possible in the system. Either it has entropy 200 or 100, it doesn't have 150.
I'm saying if you also include the bath, then
No, you don't have to include. You can talk of the bath entropy separately.
but that's like a one full process.
You wish, but we are talking of one component at a time. That component may be big, and there may be rest of the universe, but we don't worry.
So you're saying that, okay, the system breaks into different sectors, and each sector there is some...
No. So this, we are only discussing the entropy of the sector just now. Sorry, entropy of the system, not of the sector. Okay. So I haven't got into the inside, and I haven't shown you what are the states available. I'm just saying there is a pot full of water. What is its entropy?
No, but I mean, if you're saying that there is entropy as a distribution,
Huh?
so but distribution comes from what? What's the random variable there?
The random variable is the protocol I used. With probability half, I gave it lot of heat. With probability half, I gave it less heat. Okay. So the macro states can be distinct in non-equilibrium systems, and then it should be possible to give, say, that the macro state has an entropy and this entropy has a distribution. Sorry? We come to it that point. Okay, calculation of entropy. Here we use the general formalism for the Sokoban problem. You know, these problems can be extended further, but we just show it in this case. There is some arbitrariness in definition of breakup of phase space into inequivalent regions in the general definition given by Goldstein et al. There is some freedom. In our case, we will use the ILCC as macroscopically indistinguishable parts. So I've told you, I can prepare a system in some non-equilibrium state. It's not in the maximum, like, you know, not after a long time. So maybe it has some contractible spaces still there. But I know their density. That's a macroscopic characterization. So in this sense, I know the level. And then within the level, there are lots of these connected parts. Then I stay in one connected part. And I would say that, okay, I don't know where it is exactly in this connected part. I only know the macroscopic observable. And I know that it's in only one part. Okay? So we will use ILCC as macroscopically indistinguishable part by definition. To each configuration, we define the non-ergodic entropy as log of the size of the ILCC to which that configuration belongs is defined for each configuration. And so consider a configuration like AF, AF, AF. And so F's are just statics, they don't have any contribution. But A can be in lots of configurations, which is omega of A. And the full answer is product of these. Omega A is the number of configurations of this single active region that can be reached from one particular value A1. Okay? And a log is sum of logs. And so if you take expectation value of this, then it becomes probability that you will find one particular active segment multiplied by log of the number of components in that segment. In our model, the randomly chosen configurations in the limit of large L, AI are independent random variables. S non-ergodic is a sum of independent random variables by central limit theorem. Its distribution is Gaussian with variance proportional to L. In the ensemble, we can write down the probability of each L and the corresponding number of configurations. Forget this. The sum over the configurations is exponentially converged. So this summation, which we wrote down here, this one. For large A, this becomes very small. So this is a series which you can sum numerically. And we find that this is non-ergodic in our problem is this number. It's the most likely value of this thing. And similar calculation can be done if you specify additional observables. And so we generate at random 10 to the power 5 configurations for L equal to 1000. For each configuration, you can calculate the entropy and look at the distribution. It's a Gaussian. And if you do with 5000 and rescale with S minus LS bar divided by root L, they sit on top of each other. So it's it's not a surprise, but the central limit theorem is working here for our problem. So let us consider now a system evolving from a specific initial condition at time t equal to 0. We consider changes in entropy of this single realization as the system evolves step by step. So it's the important point here is that I am having one system, it's evolving once. There is no ensemble. If the system jumps from over one configuration to another within the same ILCC, the entropy doesn't change because the ILCC is the same. If it goes to a different configuration, then it pushes out something, then the entropy will increase. The accessible region becomes bigger. And so this S non-ergodic will increase. And here is a graph of S non-ergodic per site as a function of height h. Height can only decrease, so and the entropy goes up, the graph goes to the left. For 3 different initial conditions, you get different graphs. For the same initial condition, we plotted it 3 times, evolved it 3 times, then you don't get exactly the same evolution, but it's close. And so this is the summary. We studied the non-ergodic and non-ergodicity and phase space breakup in a model of Sokobans. This model can also be studied in higher dimensions. We have some preliminary results of simulations in 2D. And you can also study it in this random layer tree-like graph, which has a dimension d equal to infinity, where the Bethe approximation can give some exact answers for some things. If we define the rate of jump as non-zero, so viewed at height, suppose you allow people to go up instead of only going down. Suppose the Sokobans can always pull with some lower rate, then it becomes equal to a problem with temperature finite, and it becomes closer to the spin glass problem, say at finite low temperature, and then this can be pushed further. But okay, let me stop here.
Yeah, so at some sort of broader, cruder level, what does this entropy, this non-ergodic entropy really capture? Because you've got these regions that are stuck, and that is a characterization of sort of the landscape, if you like.
Yeah.
And we understand what equilibrium entropy, captures, but
so we are actually trying to quantify this particular picture, which is very old, and we are sort of making an example in which you can actually calculate the number of minima and the sizes of basins, which is usually not easy to do. So the entropy is just the entropy as would be seen in some experiment in a glassy system. So people do specific, they take some liquid glass and they cool it down. It doesn't become crystalline, but you can measure specific heat along the way, and you can calculate observed entropy of the glass. This is what we are doing. It's a non-equilibrium entropy, and it can evolve in time.
Just a very naive question. So when you say observed entropy,
Huh.
it means that they're really integrating delta Q over T.
Yeah.
They're taking thermodynamic books
Yeah.
and doing that, calorimetry.
Presumably some such thing, yeah.
Okay. And I had another question, again, very nice, sorry, I'm so asleep. You said that there's this Goldstein definition that entropy is something accessible within reasonable time. And then
Yeah.
you showed this graph where you have these different different disconnected components, and you go down to the zero level.
Yeah.
So have you supposed that within a given level, it goes fast, and then it takes time to go to the lower level?
Yeah, we
Something
are
like that?
taking that picture and we are assuming this much. So what happens is that in standard equilibrium state mech, the number of states available at any given time is very, very large. The system does not sample all the states, or it takes, Poincare recurrence time kind of time. But the states it's able to sample are as good as representative, and the ensemble average over all states is the same as that over the small part you sample. This is what we assume, that even though it will not sample all states in the ILCC, whatever it can sample is as good as the average over the full ensemble.
And maybe last question, this entropy, thermodynamic entropy that you said is not the right one. So it's a kind of average of all these entropies for all the levels?
No. So thermodynamic we didn't deal with explicitly here, but no, thermodynamic entropy is the right one, which is the experimentally observed quantity, which we try to explain. And the claim is that this kind of prescription will be able to do, whatever is the definition I gave here. That one.
Yeah,
This
that's
definition will actually work and give the correct answer for glassy
for
systems.
experiments.
Yeah.
Okay. And the equilibrium one has no real meaning.
Because I'm
It's
not
never
in
reached.
equilibrium, I don't know what it is. It will be something which is inaccessible, So if you have diamonds, it'll give you the entropy of graphite or some such thing.
Also a stupid question, maybe. Liking lattice gases with constrained dynamics,
Yeah.
will you have here a kind of a population splitting? So you will have some domains in space where soccer bonds have very favorable for them configurations and they will operate very quickly. But some regions in which they will get stuck and
Yeah.
so you will have a huge disproportionality in the behavior.
Yeah, so that is called heterogeneity, dynamical heterogeneity or some such thing. It requires you to look deeper inside the system. I actually tried not to do it. I just look at the Sokoban. I don't look inside how they are evolving, who is pushing what where.
But intuitively, do you believe that it will take place here?
Of course, in the model it is happening. I cannot stop it. But I'm not observing it in great detail.
So you're talking about this here, should be
Yeah.
reasonable time for the definition
Yeah.
of entropy. So for different reasonable times, the entropy will be different. So will they be proportional
Yes
to
and
each
no.
other, or
No. Of course, it is going to be different sometimes. But what happens in experimental situations often is whether you do it for 1 hour or 3 hours, it doesn't change. And that's what we mean by reasonable time. If you wait for 3 years, it will change. Yes, sir.
Just because the phase space breaks up into ergodic sectors, it is better to talk of probability of having entropy than entropy average.
Actually, that is sort of what has been said all this time before. So this picture is actually very, very old, but it is actually not very good for the reason you are not always at the minimum. You have a finite temperature, so you can go above the minimum. How far above? Can I jump to here? Yes, sometimes you can jump, sometimes you cannot jump. So if you say that you are in some region, it's not clear where you will stop the summation. Okay? And that is the sloshiness in the definition which people push under the carpet. But that is what we are trying to address here. Of course, it's sort of a contrived system, so the definitions are quite clear and clean. In a real quartz or glass, I will not know where to stop the summation, but that's the point. The point is that you sum over states nearby one minima, but where do you stop is not clear, and so this picture is not, it doesn't tell you that you should sum over many states near this minima. And if there are other people who talk of free energy landscape, that's even more dangerous, because it is not clear. There they say sum over states, but there the question of where do you stop the summation is not addressed at all.
Sorry again, another question. Orthogonal to your message, I understand it will be in fact orthogonal, but you're not talking at all about invariant measure. I know it's not.
No. So here in this model, we have discrete space, so the measure is just the number of states.
Okay, all the simple states.
All states are equally likely by definition
Okay.
in the microcanonical ensemble.
Last question.
Deepak, do you know something about how much time it takes the system to go to the maximal entropy state? So this coarsening happens.
Yeah, so these are many Sokobans, they are pushing around. Once in a while they keep pushing in and decrease the entropy. So the time is proportional to L. The total time to go from top to down, is the number of steps is proportional to L. In real time it will be finite, because there are L different people pushing. It's 10 or some such thing. It's not very much in this model.
How far, given that Sokoban displaces, if you think again in the analogy with the tracer diffusion,
So in this model
in
here,
single file dynamics.
yeah, just 1 minute. So in this model, they just stay in one connected region, no? This one. It will, the Sokoban can only stay between this yellow and this yellow.
So it will be localized.
It will be of order 1, it's perhaps 10. The mean spacing between, mean length of an active region in our model is 12.
Okay, so let's thank Deepak again for. So next speaker is Devashish
yeah.
from Institute of